So this lesson is going to be an introduction to the process of titration, which is analyzing mathematically the reaction of an acid with a base. And so what we need to do, we're going to be given a lot of situations in which you might have more acid that's being added than base, or more base that's being added than acid. And so what I've done is I've created some rules that we're going to go over to help you to analyze these problems. The first thing that I want to introduce you to, though, is this formula called the Henderson-Hasselbalch equation. Now, this equation will be liquid gold, and the reason why it is so amazing is because it allows you to calculate the pH of a solution if you know the concentration of base and the concentration of acid that exist at equilibrium. So if you're given, if you know the concentration of both base and acid, you do not have to use an ice chart to figure it out. All you have to do is plug it into this equation. So we'll get lots of practice with this as we're moving along. This equation will be given to you on the AP, by the way. Okay, so here are the rules that I came up with in order to try and make these types of problems make more sense. The first one, if you have extra strong base, so it doesn't matter if you are reacting that strong base with a weak acid or a strong acid, it doesn't matter. Hydroxide ions, all you have to do is use that concentration of hydroxide ions to calculate the pOH. That's it. Because at that point, you don't have any more acid left over. Therefore, you can just use the concentration of OH to calculate pOH. Same thing, very similar with a strong acid. Doesn't matter if you're reacting it with a weak base or a strong base. If you have excess strong acid, what that means is that all you need to do is use the concentration of hydrogen ions now that are left over to calculate the pH. Okay? Now, if you have excess weak base, what you need to do is you need to figure out how much base is left over and how much conjugate acid is formed. Then, because you'll know the amount of base and the amount of conjugate acid, you can use your Henderson-Hasselbalch equation. And we'll get practice with this, I promise. For excess weak acid, again, figure out how much this time acid is left over and how much conjugate base is formed, and then you can use the Henderson-Hasselbalch equation. Finally, if you have the same amount of acid and base, well, if your acid and base are strong, you automatically know, if you have equal amounts of the two, that your pH will be 7. Now, if one of them is weak, then you have to determine the pH of the solution by looking at the salt, which is what we did in the previous lesson. Looking at salts, figuring out whether they're going to form basic solutions or acidic solutions, using ice charts and calculating the pH. All right? So the easiest problems that you'll be dealing with are number 1, number 2, or number 5 if it's a strong acid and a strong base. Number 3, number 4, and the second part of number 5 are not extremely challenging, but they do require some work, and so that's why I'm dedicating this entire lesson to this concept. So let's look at a bunch of practice problems, and then you'll work on practice problems in class. All right, so first example problem. It says calculate the pH when 24.9 milliliters of 0.100 molar nitric acid, so that's a strong acid, is added to 25.0 milliliters of 0.10 molar KOH. Well, potassium hydroxide is a strong base. So this is a strong acid and a strong base. Keep in mind, before you even get started, because you are adding two concentrations, two solutions together, you need to find the new concentration once they're mixed together. So in this, I'm going to show you one example of it, but for the rest of the time, I'm going to assume that you can do it. So for the nitric acid, the initial concentration is 0.100 molar, okay? That equals the however many moles, I'm not sure, divided by the initial volume in liters. So I move that decimal place over 3 places. So I can find the number of moles of nitric acid really easily. It's 0.00249 moles. To find the new concentration, what I need to do is I now need to divide that by the total volume, which is now going to be 49.9 milliliters because I added the two volumes together, or 0.0499 liters. And so the concentration I get for nitric acid is 4.99 times 10 to the negative second molar. I'm going to do the same thing, but now for potassium hydroxide. So I'm going to take 0.100 molar of potassium hydroxide. I'm going to multiply that by 0.0250 liters, because that's its volume, and then divide that number of moles by the 0.0499 liters. And what I get for potassium hydroxide is 5.01 times 10 to the negative second. So here's the key part. What type do I have? What do I have excess of? Well, if you look here, I've got excess strong base. So all of the nitric acid is going to be used up, okay? And the only thing that's going to be left over is hydroxide. And so as a result, what I need to do, this is a number 1 example, okay? What I need to do is subtract, find the difference between their concentrations, and that is going to be the amount of excess hydroxide that's left over. So the amount of hydroxide that's left over is 2.0 times 10 to the negative 4th molar, okay? I don't have any acid left at all. And so what I can do is find the pOH by taking the negative log, and I find it to be 3.70. And then to find the pH, just do 14 minus that, and there's my answer. Okay, so that one's really not that bad. Let's look at another example. Here I'm given acetic acid and sodium hydroxide. So I've got a weak acid and a strong base. So again, the first thing I've got to do is to find the new concentrations once they're mixed together. So when you do that, it would be 0.150 molar for acetic acid times 0.035, and that gives you the number of moles, and then divide that by the total volume, which in this case is going to be 69.5 milliliters. Okay, so divide by 0.0695, and what I get for my concentration of acetic acid is 0.0755 molar. Make sure that you're able to do this calculation, guys, and if you're needing help, please come in. Okay. For the hydroxide, I get 0.0745. So now here's the analysis time. What is going on? Well, what's going on is that I have excess acetic acid. Okay, and so the type of problem that this is going to be a number 4. I've got excess of a weak acid, and so what I'm going to do is I'm going to analyze that weak acid. That weak acid is what is being left over. So here, I've got a number 4. So what I need to do is figure out how much of my weak acid is going to be left over from this reaction, and then how much of its conjugate base is going to be formed. So I need to actually write out this reaction. So I've got my acetic acid reacting with, well, a strong base in this case. So I'm going to just write the hydroxide ion, and it's going to produce acetate ion and water. Okay, I'm going to ice this really quickly. I know my concentration of acetic acid is 0.0755. My concentration of hydroxide is 0.0745. 0 for acetate, and I don't care about water. So the amount that the concentration is going to change by is 0.0745, because that's all the hydroxide that I have that can react. So I'm going to subtract 0.0745 here, subtract 0.0745 here, and then add 0.0745 here. And so what I end up getting is that concentration for my acid and that concentration for my conjugate base. And what I can now do is plug this into my Henderson-Hasselbalch equation to calculate my pH. So this is the equation. My pH equals my pKa, which is the negative log of my Ka, just like pH is the negative log of hydrogen ions. So I'm going to do the negative log of 1.8 times 10 to the negative 5th plus the log of my base, which is 0.0745, divided by my acid, which is 0.0010. And so when I calculate this, when I do all of this math, I end up getting my pH, which is 6.61. Okay? So by figuring out how much of your acid is left over and how much of your conjugate base there is, what I'm meaning is actually show the reaction, show all of your strong base being used up, and then figure out how much of your weak acid and your weak base are going to be present at equilibrium, and therefore you can use your Henderson-Hasselbalch equation. Let's look at another example. Okay, here I have the same problem, except I start with 35.0 milliliters of sodium hydroxide, not 34.5. So again, I've got to recalculate my concentrations once they're mixed. My new concentration is 0.075 molar and 0.075 molar. So this case, since they're equal, I have a number 5 on my hands. Unfortunately, because acetic acid is not a strong acid, this is not going to just be neutral at equilibrium. Instead, I've got to figure out what salt is going to be produced, and as a result, what the pH of the solution. Okay? So I know that when acetic acid and sodium hydroxide or hydroxide react, what's going to be formed is my acetate ion and water. Okay? So now what I'm going to do, I'm going to create my ice chart. Okay? I know, since I have 0.075 molar here and 0.075 molar of my base, 0 of acetate, we don't care about water, since it's going to change by 0.075 for both of my reactants and add 0.075 for acetate, my concentration of my acetate ion is going to be 0.075 molar. Okay? So this is my salt. My salt would be, if I hadn't ignored the sodium, it would have been sodium acetate, NaC2H3O2. But I ignored the sodium, so I've just got my acetate ion, which makes it a lot easier. Question, is this going to act as an acid or a base? Well, obviously it's a very familiar example here, but this is going to be a weak base because it's the conjugate base of acetic acid. So acetate is going to react with water, because this is it acting like a base, to produce acetic acid and hydroxide. So what you're going to do now is plug in the 0.075 here. I'm ignoring the water. I don't start off with any acetic acid, and I don't start off with any hydroxide. Okay, so this is just a weak base problem, so I'm going to subtract x, add x, add x. What I end up getting is 0.075 minus x, x and x. Okay. I'm going to use my KB now. Notice in the previous problem I gave you Ka. So what you have to do is take 10 raised to the negative 14th and divide that by your Ka, because remember Ka times Kb equals 10 to the negative 14th. And so what I get here, my Kb, I'm going to really quickly write out my base dissociation expression. It's going to be the concentration of acetic acid times the concentration of hydroxide divided by the concentration of acetate. Okay. Now I'm going to take my Kb, which was 5.6 times 10 to the negative 10th, which I calculated. That equals my x squared, because it's x times x, divided by 0.075, because I'm going to ignore the minus x. And so what I end up getting for x is 6.48 times 10 to the negative 6. That's my concentration of hydroxide, so my pOH is 5.19, therefore my pH is 8.81. So for this problem, honestly, this type of problem, the number 5, is probably the most difficult, simply because once you show the reaction for the acetic acid and the hydroxide, you would think you would be done, but unfortunately, because you've created a conjugate base, you need to see how that would react. And that's going to act as a weak base, and therefore you need to then complete a weak base problem. However, you've already learned how to do that. So the issue with these problems is simply getting enough practice to be able to identify what type of problem you have. So this is a number 5. Let's look at another example. Here I have even more sodium hydroxide. I have 35.5 milliliters. So my concentration of acetic acid here, when I redo the concentration again, I get 0.0745 molar, and for hydroxide, I get 0.0755 molar. Now this problem is going to be easy because I end up with more hydroxide, which is a strong base. So this is going to be a number 1. I end up with a concentration of hydroxide of 0.0010 molar, and therefore I can just plug that into my pOH equation, getting a pOH of 3.00. From there, I can just find my pH. So when you have excess strong acid or strong base, the problem is really easy. The difficulty comes when you have excess of a weak acid or a weak base. I wouldn't call it hard, I would just say that it is a more involved problem. Let's do one very last question. Here I'm given a weak base and a strong acid, HCl. Okay, so I'm going to quickly find the concentrations of both of these once they're mixed. So the concentration of ammonia is going to be 0.386 molar, while the concentration of my hydrochloric acid is going to be 0.357 molar. And so automatically in my brain, I know I'm going to have excess of a weak base. Therefore, since I have excess of a weak base, I've got to figure out how much of my weak base I'm left over with and how much of its conjugate acid is going to form. So I'm going to write the reaction of ammonia with hydrogen ions. So ammonia reacts with hydrogen ions, and that's going to produce an ammonium, NH4+. Okay? So ammonium is the conjugate acid of ammonia. So I'm going to ice it. I'm going to put 0.386 molar for my ammonia, 0.357 for hydrogen ions, and 0 for ammonium. I'm going to subtract 0.357 because all of the hydrogen ions are used up, add 0.357, and what I end up getting is 0.029 and 0.357. Now, since I know the concentration of my weak base and my weak acid, I can simply use the Henderson-Hasselbalch equation. And so it's going to be my pH equals the negative log of my Ka, which was given to me. Notice my Ka itself wasn't given, it was my Kb that was given to me. So you need to take 10 to the negative 14th, divide it by my Kb, and that'll give you your Ka. I'm going to add to that the log of my base concentration, which was the 0.029 because ammonia is your base, divided by 0.357 because that's your acid. And what you get for your pH is 8.16. So after analyzing this problem, the very last thing I want you to do is to decide what type this is. Is it number 1, 2, 3, 4, or 5? And we'll discuss this in class.